So the ultimate goal for today, we're assuming n and m are natural numbers, and the ultimate goal for today is to prove that there can be an injection from n to m if and only if n is less than or equal to n. Now, I want to start with actually this direction so that we can get it out of the way. So assume n is less than or equal to m. Then our goal becomes to prove that there exists an injection from n to m. How do you prove an existence statement? Our fancy name for it is EG, existential generalization, right? But that's just a fancy name for finding an example. We need to find an example of an injection from n to m. So that's our goal. Construct an injection from n to m. Find one. Well, let's just think about small examples. So let's say n is 3 and m is 5. That would be an example of one thing that's less than or equal to another thing, and they're natural numbers. Can you find an injection from 3 to 5? And can you construct it in a systematic enough way that your construction will work regardless of what the actual numbers were? So let's see. 3, here's the set 3. It consists of 3 dots labeled 0, 1, and 2, right? So that's the set 3. And then 5 consists of, how about I not put the dots? I'll just put the label. 5 consists of 0, 1, 2, 3, and 4. Can you construct an injection from 3 to 5? Now I could do sort of random stuff. I could do this, 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 and that would certainly be an injection. Not everything I do is an injection. Like if I did this, that would not be injective, right? Because two things are going to one place. But you could easily find a random injection like this one, right? But the goal is actually to do it in a systematic way so that you can make an argument that works in general. So what would you do here? Probably just send each number to itself. That's very easy to describe, right? That would be an injection. So that's what we're going to do. And actually, it's very easy to describe sort of the formula for this. It's just 0 goes to 0, 1 goes to 1, 2 goes to 2. So it's k goes to k, right? What function is that? A function that sends things to themselves. That's the identity, right? What we're looking at is actually just the identity on 3. The identity on the set 3. So there's our injection. Now it's true, the identity on the set 3, we have said many times, maps 3 to 3, but I can also enlarge the codomain, and this is still true. It also maps 3 to any set that contains 3 as a subset. Now, when you do this, when you change the codomain, you're sort of adjusting the context of the discussion a little bit. So you could be changing whether or not you consider the function to be surjective, but you don't affect whether or not the function is injective. So we should be able to use the identity function no problem here. And this was just an example, but it will work in general. So what made this work? It was the fact that 3 is a subset of 5, right? That's what allowed this to work. So that happened with 3 and 5, but does it always happen? If n is less than or equal to m, then do you think n is a subset of m? Well, what would you do to prove that n is a subset of m? You would consider any k in n, and then you would try to show that that k is in m, right? But remember, in our particular and kind of strange way of constructing the natural numbers, k in n is just another way of saying k less than n, and k in m is another way of saying k less than m. And do you think it's true that if k is less than n, then k is less than m? Yes, when you have this, due to transitivity. Due to transitivity of less than. So now I'm just going to basically write that argument down. So assume n is less than or equal to m, then for any k less than n, we have k less than m, because you'd have k less than n less than or equal to m. And this is due to transitivity, which was theorem 100. So since k less than n is the same as saying k in n, and k less than m is the same as saying k in m, we actually have proven n is a subset of m. Now, that means the identity function on n maps n to m, right? So normally, what do we know about the identity function on n? It maps n to n, right? This is what we know just from our earlier basic facts about the identity function result back here. So we know this by that result. But then this tells us the range of the identity function. I mean, it is actually equal to n, but this just tells us that it's a subset of n. Since n is a subset of m, we have this, and so this is a subset of that. And so this is justified. Now, this is injective. I haven't really proven that anywhere. It's super easy. I kind of regret not putting it in here under facts about identity. But I think maybe injectivity was never defined at that time. Oh no, it was. That was dumb. I should have put the fact that it's a bijective function here with these facts. Anyway, here's just a quick proof, just to leave no gaps here. Suppose that you have two things in the domain of the identity, and when you apply the identity to them, you get equal things. Then to prove injectivity, we'd have to prove that in this situation, we always end up with x equals y. And we do because x is this, which we've assumed is equal to this, which is y. So very easy, the identity is injective. And so we have an injection from n to m, right? We have found an injection from n to m. So then we can say this is existential generalization. There is an injection from n to m. All right, so that proves that if n is less than or equal to m, then there exists an injection from n to m. So let me sort of move all of that out of the way, since that direction was really the easier one, and we'll shift our focus to this one.